So let's come forward a little bit and start to think about, well, what is the ramification of this in terms of collecting our data? At the moment, we've been talking about averages. So you've seen in previous slides where you can see kind of a single data point, and that single data point may be averaged if it's breath by breath data. It may be averaged across time, but more importantly, what we generally do is average across breaths. If I'm using an open circuit spirometry, what I do is I have all that expired air in a single Douglas bag, and I average across all that data in one Douglas bag. Does the way in which we average affect the outcome of our test? That is, does it affect the determination of VO2 max? Well, if we read this is a paper from Adrian Midgley, published a while back now, but really, really useful in what it describes. In their present study, they found that longer VO2 time averaging intervals tended to result in significantly lower VO2 max values. So this is, for example, if I have got data from a Douglas bag, and in a Douglas bag it is a single value, so I've got it, let's say I collected over a minute, it's a single value. But so you've got a long time averaging window. Whereas if I've got maybe I'm repeating, I've got, let's say, loads of Douglas bags lined up, and I take a sample potentially every 15 seconds, one into this bag, another 15 seconds in this bag, I've got shorter time averaging, I've got more to average over. So their argument is that you've got lower VO2 maxes with longer VO2 averaging. And it's consistent with previous findings. This time averaging effect was as high as a 4.3% difference for mean within subject VO2 max differences. And this has big ramifications to play when you're using breath by breath data. Because in a breath by breath response, you're collecting, as the term suggests, you're collecting data for each time a breath is taken. So I may well be getting in the region, to the end of a VO2 max test, I may well be getting in the region of 45, 60, 65 breaths per minute. So if I average over the minute, then, you know, that's a long time to be averaging over. If I average over the 45 breaths and do every 45 breaths, that's a long average over. But if I start to reduce it down and I reduce the number of breaths, the argument is that you actually get a higher VO2 max outcome. So we now have to ask ourselves, why might that be the case? Well, one of the reasons is that we are adding error in if we start to reduce the time averaging interval. So let me explain why that's the case. If you're averaging over a minute, think about the unit. And if you are doing an average over a minute, it's easy to understand. It's litres or millilitres per kilogram per minute. So fundamentally, I've got a minute's worth of data. That is the VO2 response for that minute's worth of data. If I now go and do 30-second time averaging intervals, I'm actually making the assumption that this 30-second here that I've collected, this first collection, refers to the second 30 seconds. Because remember, fundamentally, what happens is your data is normalized to the minute, because the units are litres per minute. So we fundamentally are going to change. We're actually adding error in. If I then go to 15-second averaging, I'm biasing the data. I'm actually quadrupling the error, because I'm making the assumption that this 15-second response is reflective of the next 45 seconds. So you can see how we may end up with a higher VO2 max, and it may not be a genuine VO2 max. It may just simply be because of the way in which I've been doing my averaging. But Midgley goes on to write this, which is quite important. Short time average intervals appear to be inadequate, though, in reducing the noise in pulmonary VO2, and therefore what we've just been suggesting may result in artificially high VO2 max values. Longer time averages may sufficiently reduce the noise, but may artificially depress the VO2 work rate relationship for incremental exercise, resulting in artificially low VO2 max. So we're at a position where the way in which we simply average the data actually affects the outcome of the test, irrespective of the protocol that you've used. And so this has big ramifications. The best approach really is to use breath averaging. And the reason for that is, with time averaging, the number of breaths changes. So once we get beyond gas exchange threshold, and we start to go through what is called the zone of isocapnic buffering, we get an increase in breathing frequency, but we get a leveling out in the tidal volume. So the breathing frequency now is the only thing that's going to be driving up the minute ventilation of your participants. So that is continually rising. So if I'm time averaging, I'm averaging over an unbalanced number of breaths within my average, because if I'm doing, say, 30-second averaging, then, well, actually what happened in this first 30 seconds is different in terms of the number of breaths for the second 30 seconds. So you are adding error into the data, so you're much, much better off, and I would strongly encourage you to do breath averaging and think about, okay, I'll concede that of the average increase in breaths changes, but what you can start to do is go, okay, what is generally the average increase of breaths once I get beyond gas exchange threshold? Because once you go beyond gas exchange threshold, that's when you get the acceleration. Find out what the average increase is per workload and start to use that as a yardstick. Doesn't mean you average to that number, but it gives you a yardstick in terms of the number of breaths that have been taken over a stage, and therefore it gives you an idea, okay, this gives me an idea how many breaths I should average over. And you can just see the difference here. This is again some data from Tad Astorino's lab. So what they've done here is they're showing the effect of using just breath by breath. There's no averaging going on here. It's a 15-second averaging, 30-second to 60-second averaging. And you can see exactly what Midgley was referring to. As you increase, and this is in time averaging, as you increase the time averaging index, you reduce the VO2 max. And it doesn't look much, right? But we've gone from about a 52 mils per kilogram per minute score here to an under 50 mils per kilogram minute score here. Now, it is within the threshold for daily variation, which is around about 5 mils per kilogram per minute daily variation. But nonetheless, we are seeing a significant difference across this range between particularly the breath by breath in the 60 seconds, but also between the 60 seconds and the 15-second tests. So it does have a ramification in terms of what we are doing.